So we're going to be continuing to discuss solving triangles. Remember that we've already defined that what we mean when we say solve a triangle is to find all of the angle measures and all of the side lengths. So it's 6 total measurements that we need to know. So we've been working with right triangles, and here we have triangle ABC, where the measure of angle B is 45 degrees, the measure of angle C is 75 degrees. We know the length of A is 7, or the length of BC, which I've called A, is 7. And if we wanted to solve this, we could easily find the measure of angle A, because we know that the 3 angles in a triangle have to add up to 180. So 45 plus 75 is 120. Subtract that from 180, and we do get that the measure of angle A is 60 degrees. But now we're stuck in terms of being able to find the length of AC and the length of AB, because this is not a right triangle. Now, it is possible for us to draw an altitude from B to AC that would give us a right triangle, and we could work with angle A being 60 degrees. But the problem there is we don't know the length of the altitude. Or if I drew an altitude from C to AB, same thing. It would give me right triangles, but I don't know the length of the altitude to be able to take advantage of that. So what we have here is actually what's called the law of sines. The law of sines is ratios involving the sines of our angles in any triangle that will allow us to find the lengths of the sides. In a moment here, I'm going to actually go through the derivation of where the law of sines comes from. But the things that are important to know here is that if we want to know the law of sines, we need to know at least 2 of the angles. So this would be for a case of if we knew angle, side, angle, or angle, angle, side. So we have to know at least 2 angles, and we have to know at least 1 side. Whether the side is included or excluded doesn't really matter. But we have to know 2 angles and 1 side to be able to use this. So where the law of sines actually comes from is, let's say we do draw that altitude from B to side AC here. Well, within triangle AB, and I'll call this D, if I say the length of the altitude is K, I could look at the sine of A is going to be opposite over the hypotenuse, which would be C. Or I could look at the other right triangle that was formed, triangle BCD, and say, let's look at the sine of C, which would be the opposite K over the hypotenuse of that, which is A. Well, I have 2 equations here. If I get K by itself in each of these, so for this equation, if I get K by itself, I would have C times the sine of A is equal to K. For this equation, multiplying each side by A, I get A times the sine of C is equal to K. Well, I can now do substitution for K and set these 2 equations equal to each other. So I would have C times the sine of A equals A times the sine of C. And now I'm going to divide each side by this length C and each side by this length A, which gives me the sine of angle A over A is equal to the sine of angle C over C. And there is our law of sines. To show this also extends to the sine of angle B over B, I would just have to draw one of the other altitudes, usually the altitude from angle C to side AB. But it's the exact same argument then. So the law of sines is allowing us to work with an altitude without actually having to find the length of the altitude. So it's a shortcut for us. So if we go back to the triangle we started with, we already said that angle A is 60 degrees. Let's say I wanted to find out what B was. What it is I'm setting up ratios of sines of angles to the lengths of their opposite sides. So if I'm looking at the sine of A, angle A, to the length to the side opposite it, that's the same as the sine of 60 degrees, and the side opposite is 7. If I'm looking at angle B, the sine of angle B to the side opposite it would be the sine of 45 degrees to the unknown B that we have. Or if I look at angle C, I have the sine of C compared to the side opposite it. So that'd be the sine, I should be consistent in my notation here with arrows. I'd have the sine of 75 degrees to the side opposite it, which is C. And what the law of sines is saying is that all of these ratios are equal. So if I want to find B, I just need to set its ratio equal to the one that I do know. So I could say that sine of 60 degrees compared to the 7 is equal to the sine of 45 degrees compared to B. Well, then I can cross multiply, so I'd have B times the sine of 60 equals 7 times the sine of 45. Divide each side by the sine of 60 degrees. I get B equals 7 times the sine of 45 degrees divided by the sine of 60 degrees. And if I work that out, I get that B is equal to 5.715. Then if I want to find out what C is, I can take the ratio of angle C to its opposite side, sine of 75 degrees to C, and say that has to be equal to either the sine of 60 degrees to 7 or the sine of 45 degrees to the 5.715. I'm going to go with the sine of 60 degrees compared to 7, just because it's going to be easier numbers to work with. Cross multiply, so I'd have C times the sine of 60 is equal to 7 times the sine of 75. Divide each side by the sine of 60 degrees. Oh, not 60 degrees. Sorry about that mistake. Yeah. Actually, yeah, I'm sorry, that's correct. Yeah, sine of 60 degrees. Divide each side by the sine of 60 degrees, and C is going to be 7 times the sine of 75 degrees divided by the sine of 60 degrees. And when I work that out, I get that C is going to be equal to 7.807. And there is our law of sines.